Welcome to Simerics. This presentation demonstrates virtual testing of a single piston pump and valves using the computational fluid dynamics software PumpLinx. This system consists of a single piston moving with a prescribed motion and two valves which open and close in response to the fluid flow. It is part of a multi-stage high-pressure pump commonly used in the oil and gas industry. This demo models a single stage of a multi-stage pump. However, PumpLinx could efficiently model the complete multi-stage device. Virtual testing has distinct advantages over physical testing. It's faster, less expensive, and provides more insight than hardware testing. Using PumpLinx, the analysis provides the pressure, velocity, temperature distributions, the generation of bubbles due to aeration and cavitation effects, and integrated quantities such as loads, torques, power, and other characteristics relative to the fluid system. Perhaps the most important advantage is that using virtual testing, flow information is available at every location in the system rather than just a few sensor locations. Model setup begins with the CAD surfaces, which describe the unsimplified geometry. This is then used to generate the model. Next, the fluid properties and operating conditions are specified, similar to how a real hardware test would be set up. The flow solver is then launched and the simulation is generated. These are the various components of the system. Fluid comes in at 1 atmosphere and is pumped out at 100 atmospheres. The pump is driven by an engine, and the spring-loaded valves control the direction of the flow. Here we see the flow field colored by velocity magnitude, seeded with massless particles for flow visualization. Bubbles are formed in the piston chamber and under the valve outlet due to the pressure drop during the expansion stroke as the fluid opens the inlet valve at the bottom. During the compression stroke, the inlet valve closes and the outlet valve is forced open by the fluid pressure. In this simulation, PumpLinx predicts the motion of the valves using the force balance of the pressure integrated over the valve surfaces, the valve mass, and the restoring spring force. PumpLinx can also model valves which are controlled by a solenoid. Here is the pressure distribution in the pump. Notice the flashes that occur when one of the valves opens or closes. This occurs because high pressure waves are generated and propagate through the system when the valves close. This is a water hammer effect. PumpLinx can output plots of pressure fluctuations anywhere in the system, as well as the displacement of the valves. The lower left shows pressure traces at 2 points in the flow field located at the red crosses above. The lower right shows a plot of displacement of the outlet valve over a small time interval. The next slide is a slow motion animation of the pressure wave traveling through the device as the valves open and close. Here is the velocity distribution. Notice the fluid jetting past the valves as they open. In this simulation, the inlet valve is modeled as if it closed perfectly, but the outlet valve was intentionally made to close only partially, which is a realistic effect. This is a close-up of the velocity distribution near the outlet valve. When the outlet valve closes, fluid leaks downward, causing the pressure to drop and bubbles to form. This type of behavior often leads to hardware damage. Here are some common sources of damage which can occur in devices with valves and other systems with high pressure gradients. Earlier, we saw that pressure waves were created when the valves opened or closed. Also, jetting occurred under the outlet valve, which led to the formation and collapse of bubbles. Finally, we saw that the outlet valve did not close completely, which caused leakage and jetting. The incomplete closing of the outlet valve was modeled this way intentionally to show how real hardware effects could be taken into account in a PumpLinx simulation. Another source of damage can occur when physical contact between components of the system occurs. Please feel free to contact us if you have any questions or if you're interested in related presentations. If you would like us to demo PumpLinx using your device of interest, please contact us and arrangements to that end will be made.